Welcome to Science for Sleep. Tonight, we will explore one of the quietest and most unsettling mysteries in modern astronomy. Tonight, we will follow the evidence for a world that may exist far beyond the edge of everything we once believed defined our solar system. A planet never seen directly, never photographed, and never confirmed through reflected light, yet one whose presence may already be written into the motion of distant objects. Tonight, we will explore Planet 9, a hypothetical world whose gravity may be shaping the outer solar system from deep, invisible darkness. For most of human history, the solar system appeared orderly and finite. The sun at the center, surrounded by planets moving in predictable paths, each orbiting in a flat, harmonious plane. This structure seemed complete, a cosmic clockwork that could be mapped, that named, and memorized. Even when new planets were discovered, they fit neatly into the existing pattern. The solar system expanded, but it did not fundamentally change. That sense of completion did not last. In the farthest reaches beyond Neptune lies a region so distant and dim that sunlight becomes little more than a memory. Here, objects move slowly, frozen in deep cold, orbiting the sun at distances so great that a single revolution can take thousands of years. This region, known as the Kuiper Belt and the scattered disk, was once thought to be little more than a debris field, a leftover remnant from planet formation. For decades, astronomers believed these distant objects followed random, loosely organized orbits, shaped only by weak solar gravity and ancient collisions. But as observations improved, patterns began to appear. Small, icy worlds far beyond Neptune were found to share strange similarities in their orbits. Their paths through space were not random. Their elongated orbits pointed in roughly the same direction. Their closest approaches to the sun clustered together in space, as if guided or shepherded by something unseen. This alignment was statistically improbable. The farther astronomers looked, the more difficult it became to dismiss the pattern as coincidence. These objects, known as extreme trans-Neptunian objects, reside so far from the sun that Neptune's influence alone cannot explain their behavior. Something else appears to be shaping their motion, something massive enough to impose order across vast distances, yet distant enough to remain hidden from direct observation. This is where the idea of Planet 9 emerges. Planet 9 is not a planet discovered through a telescope image. It is a planet inferred through gravity. Its existence is suggested not by light, but by motion. The hypothesis proposes a massive, unseen world orbiting the sun at hundreds of times the Earth-Sun distance, exerting a subtle but persistent gravitational influence on the most distant objects in the solar system. If Planet 9 exists, it would be unlike any planet we have encountered before. It would not resemble Earth or Mars or even Jupiter. Instead, it would likely be a cold, distant, slow-moving world, possibly several times more massive than Earth, yet far smaller than the gas giants. Its orbit would be highly elongated, tilted relative to the plane of the known planets, and so distant that it would spend most of its time in near total darkness. And the idea that our solar system could contain an undiscovered planet is not unprecedented. In the 19th century, the planet Neptune was predicted before it was ever seen, based entirely on irregularities in Uranus's orbit. When astronomers pointed their telescopes to the predicted location, Neptune was found almost exactly where mathematics said it would be. This success left a deep imprint on scientific thinking. It demonstrated that gravity could reveal invisible worlds. Yet Planet 9 is different. Neptune influenced Uranus strongly and clearly. Planet 9's influence, if real, is subtle, detectable only through careful statistical analysis of faint, distant objects discovered one by one over decades. The signal is not loud. It is persistent. It grows stronger as more data accumulates. The modern story of Planet 9 begins not with a planet, but with anomalies. Astronomers studying the orbits of distant Kuiper Belt objects noticed that several of them shared unusually aligned orbital elements. Their perihelia, the points where they come closest to the Sun, were clustered. Their orbital planes were tilted in similar ways. Over time, the number of such objects increased, strengthening the case that something systematic was at work. Simulations offered a possible explanation. When a massive planet was placed far beyond Neptune in computer models, the strange orbital alignments naturally emerged. The hypothetical planet acted as a gravitational shepherd, trapping distant objects into stable configurations that matched observations. Without such a planet, the observed patterns were difficult to reproduce. This proposed planet was given a provisional name, Planet 9. The name itself reflects uncertainty. It does not assert existence. It suggests possibility. It acknowledges that what is being described is not yet a confirmed world, but a solution to a problem. Planet 9 exists, for now, as an explanation, a mathematical presence, a gravitational shadow cast across the outer solar system. If real, Planet 9 would force a redefinition of the solar system's architecture. For centuries, planets were thought to occupy a relatively compact region around the Sun. Even Neptune, once the outermost known planet, orbits at a distance where sunlight still reaches with enough strength to illuminate clouds and storms. Planet 9 would reside far beyond this region, in a realm where temperatures approach absolute cold and solar influence weakens dramatically. At such distances, a year would last thousands of Earth years. The Sun would appear as a bright star rather than a disk. Seasonal changes, if they exist at all, would unfold on timescales longer than recorded human history. Planet 9 would be a world defined not by day and night, but by deep time. The implications extend beyond planetary science. If Planet 9 exists, it raises fundamental questions about how the solar system formed. Standard models of planet formation struggle to explain how a planet of several Earth masses could end up so far from the Sun. Did it form closer in and migrate outward? Was it scattered by interactions with Jupiter and Saturn? Or was it captured from another star system during the Sun's early years in a dense stellar nursery? Each possibility carries profound consequences. If Planet 9 formed near the giant planets and was ejected outward, it would suggest a far more chaotic early solar system than previously believed. If it was captured from another star, it would mean the solar system contains an alien world, born elsewhere and adopted by the Sun. If it formed in place, it would challenge existing theories of planet formation at extreme distances. Planet 9 also provides a possible explanation for another mystery: the unusual tilt of the Sun's rotational axis relative to the plane of the planets. The Sun's equator is tilted by about 6 degrees compared to the average orbital plane of the known planets. This misalignment has long puzzled astronomers. A distant, massive planet on a tilted orbit could, over billions of years, torque the entire system, gradually shifting the Sun's orientation. This slow, cumulative influence fits the nature of Planet 9's proposed orbit. Its power would not come from sudden interactions, but from patience, from gravity applied gently, relentlessly, across deep time. Despite the growing body of indirect evidence, Planet 9 remains unseen. Telescopes have scanned large regions of the sky without finding it. But the search is difficult. At extreme distances, even a large planet reflects very little sunlight. It moves slowly against the background stars, making detection challenging. Its position in the sky is uncertain, constrained only by simulations and statistical models. This uncertainty has led to skepticism, and rightly so. Science advances not by belief, but by evidence. Alternative explanations exist. Some researchers argue that observational bias may create the appearance of orbital clustering. The regions of the sky most thoroughly surveyed may naturally produce apparent patterns. Others suggest that collective gravitational effects among small bodies, rather than a single large planet, could generate similar alignments. These debates are active, unresolved, and healthy. Planet 9 sits at the frontier between detection and inference, where data is sparse and interpretation matters. Yet, even skepticism acknowledges something unusual. The outer solar system is not as random as once believed. Whether Planet 9 exists or not, the distant regions beyond Neptune hold structure, memory, and complexity that demand explanation. The idea of Planet 9 forces a shift in perspective. It reminds us that the solar system is not a finished map, but an evolving hypothesis. That absence of evidence is not evidence of absence, especially when distance and darkness conspire against detection. As we continue, we will move deeper into the evidence itself. We will examine the specific orbital patterns that led to the Planet 9 hypothesis, explore how simulations reveal hidden gravitational influences, and explain why these distant objects behave the way they do. Planet 9 may or may not exist, but the mystery it represents is real. It is a reminder that even in our cosmic backyard, there are regions still unexplored, forces still unaccounted for, and worlds that may be shaping our system from beyond the edge of sight. In the next part, we will begin tracing the clues written into the motion of distant objects and follow how gravity leaves fingerprints long after the object itself remains hidden. When you're ready, say "Next," and I will continue with Chunk 2. Next, here is Chunk 2, continuing seamlessly from Chunk 1. Pure paragraph style, scientifically accurate, calm documentary voice-over tone, no lists, no narration cues. To understand why Planet 9 was proposed at all, it is necessary to look carefully at the region where the mystery begins. Far beyond Neptune, past the classical Kuiper Belt, lies a population of objects so distant that their discovery pushes the limits of modern astronomy. These objects are small, icy remnants from the formation of the solar system, preserved in extreme cold and darkness. Individually, they are unremarkable. Collectively, they tell a story that challenges assumptions about the solar system's structure. These distant bodies follow elongated, tilted orbits that carry them far from the sun for most of their long journeys. Some take 10,000 years or more to complete a single orbit. At such distances, even Neptune's gravity becomes weak, raising an immediate question. What keeps these objects from being randomly scattered by galactic tides, passing stars, or the accumulated effects of time? Why do some of them appear to move in coordinated ways? As astronomers cataloged more of these extreme trans-Neptunian objects, patterns began to emerge that were difficult to ignore. Several of the most distant objects shared remarkably similar orbital orientations. Their long axes pointed in roughly the same direction in space. For their closest approaches to the Sun occurred on the same side of the solar system. This was not a subtle resemblance. It was a pronounced clustering that stood out clearly once enough data had been gathered. The statistical significance of this clustering became the focus of intense scrutiny. Early on, researchers considered the possibility that observational bias might be responsible. Telescopes do not survey the sky evenly. Certain regions are observed more frequently, and faint objects are easier to detect when they are closer to the sun. These factors can create artificial patterns. To address this, astronomers modeled the survey biases carefully, asking whether random distributions filtered through real observing constraints could produce the same alignments. The results suggested otherwise. While bias could account for some degree of clustering, it could not easily reproduce the full set of observed orbital similarities. The probability that these alignments arose by chance remained low. The more objects were added to the sample, the more persistent the pattern became. Another feature added weight to the mystery. Many of these distant objects possessed orbits that were not only aligned, but dynamically stable. Over billions of years, gravitational interactions should have scrambled their orientations, unless something was actively maintaining order. Simulations showed that without an external influence, the observed configurations would disperse relatively quickly on cosmic timescales. This is where gravity enters the story again. When researchers introduced a hypothetical massive planet into their models, the results changed dramatically. A planet several times more massive than Earth, orbiting far beyond Neptune on a highly elongated and inclined path, naturally produced the observed alignments. The distant objects became trapped in resonant configurations, their orbits confined and shepherded by the unseen planet's gravity. These simulations did more than match the known data. They predicted additional behaviors. They suggested that Planet 9 would create a population of objects on extremely tilted or even perpendicular orbits, relative to the plane of the planets. Some objects might even orbit the Sun in the opposite direction. Remarkably, astronomers had already begun discovering such objects, lending further support to the hypothesis. The proposed planet's orbit itself is extreme. Unlike the nearly circular orbits of the known planets, Planet 9's path would be highly elliptical, carrying it hundreds of astronomical units from the Sun at its farthest point. Its orbital plane would be significantly tilted relative to the rest of the solar system, making it a gravitational outsider even among planets. This configuration explains why Planet 9 has remained hidden. At its farthest distance, it would reflect so little sunlight that even the most powerful telescopes would struggle to detect it. Its slow motion against the background stars would make it easy to overlook. Its sky position would be uncertain, spread across a vast region. Importantly, the Planet 9 hypothesis does not rely on a single piece of evidence. It draws strength from convergence. Orbital clustering, dynamical stability, unusual inclinations, DAR and long-term simulations all point toward the same solution. Each line of evidence alone might be dismissed. Together, they form a coherent picture. Still, coherence is not confirmation. Science demands restraint. The history of astronomy contains examples where anomalies were explained by new physics rather than new objects. Before Einstein, discrepancies in Mercury's orbit were attributed to a hypothetical planet called Vulcan. Vulcan did not exist. The anomaly was resolved by a deeper theory of gravity. This lesson looms large in the Planet 9 debate. Could the observed patterns arise from collective gravitational effects among small bodies? Could the galactic tide, combined with passing stars, sculpt the distant solar system in ways not fully understood? Could long-term observational bias still play a role? These questions remain open, and active research continues to test them. What sets Planet 9 apart from past speculative planets is the breadth of its explanatory power. It does not explain just one anomaly, but several, across different populations of objects. This breadth makes it compelling, even as uncertainty remains. The search for Planet 9 is therefore not just a hunt for a missing planet. It is a test of how well gravity is understood in the outermost reaches of the solar system. It probes whether current models capture the full complexity of long-term dynamical evolution under weak forces. As surveys expand and telescopes improve, more distant objects are being discovered. Each new object acts as a data point, refining or challenging the hypothesis. If the clustering persists and new predictions are confirmed, the case for Planet 9 strengthens. If the pattern dissolves, the hypothesis will fade. This process is slow, deliberate, and exacting, reflecting the vast timescales and distances involved. The outer solar system does not reveal its secrets quickly. It demands patience equal to the depth of space it occupies. To imagine Planet 9, astronomers must rely on indirect clues rather than images. Its proposed properties emerge from simulations that best reproduce the observed structure of the distant solar system. These properties do not describe a familiar world. They outline a planet that occupies a category between the terrestrial planets and the gas giants, existing in an environment unlike anything else orbiting the Sun. Current models suggest that Planet 9 would be several times more massive than Earth, and likely between 5 and 10 Earth masses. This places it in a class of planets often referred to as super-Earths or mini-Neptunes, objects that are common around other stars but absent from the inner solar system. Unlike Earth, such a planet would not be rocky in the conventional sense. It would likely possess a dense core surrounded by thick layers of volatile materials such as hydrogen, helium, water, methane, and ammonia. At such extreme distances from the Sun, temperatures would be extraordinarily low. Surface conditions, if a solid surface exists at all, would be dominated by deep cold, with atmospheric gases frozen into exotic ices. Any atmosphere would be thick, heavy, and slowly evolving, shaped not by sunlight, but by internal heat left over from formation. In this environment, because weather as we understand it would be nearly non-existent, unfolding on timescales far longer than human observation. The planet's orbit would be as unusual as its composition. Rather than following the relatively flat plane traced by the known planets, Planet 9 would travel on a highly inclined path. Its orbit would also be elongated, bringing it closer to the Sun at perihelion and then carrying it far outward into the distant darkness at aphelion. One full orbit could take between 10,000 and 20,000 Earth years. This extreme orbit explains much about Planet 9's influence. When it passes closer to the Sun, its gravity interacts more strongly with distant objects, shaping their orbits. When it retreats to the far reaches, its influence weakens but does not vanish. Over millions and billions of years, these repeated interactions sculpt the structure of the outer solar system in subtle but persistent ways. The tilted orbit also hints at a turbulent past. Planets typically form within flattened disks of gas and dust, inheriting the disk's orientation. A highly inclined orbit suggests disruption. Something must have altered Planet 9's path early in the solar system's history. This disruption could have come from gravitational interactions with the giant planets, from passing stars, or from conditions present when the Sun was still embedded in its birth cluster. One possible origin scenario proposes that Planet 9 formed closer to the Sun, near the region where the giant planets were assembling. During this chaotic era, interactions between Jupiter, Saturn, Uranus, and Neptune could have scattered Planet 9 outward. In most cases, such scattering would eject a planet entirely from the solar system. But in rare circumstances, a planet could be thrown into a distant, stable orbit instead of being lost. Planet 9, in this scenario, would be a survivor of near ejection. Another possibility is capture. When the Sun was young, it likely formed within a dense cluster of stars. Close stellar encounters would have been more common. During one such encounter, the Sun could have captured a planet that originally formed around another star. This captured planet would naturally possess an inclined and elongated orbit, consistent with Planet 9's proposed characteristics. If true, Planet 9 would be an interstellar immigrant, a world not born with the sun. A third scenario suggests in-place formation, though this is the most difficult to reconcile with current models. At extreme distances, the protoplanetary disk would have been thin and slow-moving, making planet formation inefficient. To build a planet several times Earth's mass so far from the sun would require conditions not typically expected. This possibility, while not ruled out, challenges conventional understanding of how planets assemble. Each formation pathway carries implications beyond Planet 9 itself. If scattering is responsible, it implies a more violent early solar system. If capture occurred, it suggests that planetary systems exchange material more readily than previously thought. If in-place formation is possible, it would expand the known range of planet formation environments. Regardless of origin, Planet 9's mass would allow it to retain internal heat. Radioactive decay and residual energy from formation would provide warmth deep within its interior. This internal heat could drive slow geological or atmospheric processes, even in the absence of significant sunlight. The planet would not be geologically dead, but its activity would unfold at a pace dictated by cold and distance. Planet 9's interaction with the solar system would be almost entirely gravitational. It would not produce bright auroras, visible storms, or reflective cloud bands detectable from Earth. Its presence would be felt through motion rather than light. This makes it a fundamentally different kind of discovery from past planets, one revealed through influence rather than appearance. The search for Planet 9 therefore focuses on narrowing down where it could be. By tracing the orbits of distant objects backward and forward in time, astronomers constrain the region of sky where the planet is most likely to be found. This region remains vast, spanning thousands of square degrees, but it is shrinking as data improves. Telescopes capable of detecting faint, slow-moving objects are being brought to bear on this search. Unlike traditional planet searches that rely on brightness, this hunt depends on patience. The planet's motion across the sky would be subtle, detectable only through repeated observations over long periods. This requirement makes discovery difficult, but not impossible. The possibility that Planet 9 exists highlights how incomplete the solar system's inventory may still be. Even after centuries of observation, even after spacecraft visits and detailed surveys, there may remain large objects in distant orbits awaiting detection. This realization reshapes the perception of our cosmic neighborhood. The search for Planet 9 is shaped as much by technological limits as by astronomical theory. Unlike planets closer to the Sun, which can be detected through reflected light or direct spacecraft observation, a distant object hundreds of astronomical units away presents a fundamentally different challenge. At such distances, sunlight is extremely weak, and even a large planet reflects only a tiny fraction of what reaches it. Detection becomes a problem of sensitivity, patience, and scale. Modern surveys searching for Planet 9 rely primarily on wide-field telescopes capable of scanning large portions of the sky repeatedly. These instruments are designed to detect faint objects and track their motion over time. Because Planet 9 would move very slowly against the background stars, its motion could be easily confused with distant galaxies or noise unless observations are carefully repeated and compared across months or years. One of the key difficulties is uncertainty in the planet's orbit. While simulations constrain possible regions of space, they do not point to a single location. Planet 9 could be anywhere along its elongated path, and depending on where it is in its orbit, it could be significantly closer or farther from the Sun. When closer, it would appear brighter and easier to detect. When farther away, it could be almost invisible to current instruments. This uncertainty means that astronomers must search vast regions of the sky, often focusing on areas where simulations predict higher probability. Even then, the search is time-consuming. Each candidate object must be observed multiple times to confirm motion consistent with a distant solar system body rather than a background star or galaxy. Infrared observations provide another avenue. A planet retains heat from its formation and emits infrared radiation even in deep cold. However, at the proposed distances and temperatures, this emission would be extremely faint. Past infrared surveys have placed constraints on the size and temperature of any undiscovered planet, ruling out very large or hot objects, but leaving room for a colder Earth to Neptune mass world. As surveys improve, the parameter space where Planet 9 could hide shrinks. Each null result does not weaken the hypothesis automatically, but it does refine it. The planet, if it exists, must fall within increasingly narrow bounds of brightness, mass, and distance. This process mirrors how Neptune was eventually located, though on a much more challenging scale. The discovery of additional distant objects continues to play a central role. Each new extreme trans-Neptunian object provides another test of the hypothesis. Their orbits either strengthen the clustering pattern or weaken it. Over time, statistical confidence grows or fades accordingly. This incremental accumulation of evidence is essential in a field where direct detection is difficult. Importantly, Planet 9 is not required to explain all features of the outer solar system. It is a solution to specific anomalies. If future data show that those anomalies disappear when observational bias is fully accounted for, the hypothesis will be discarded. This possibility is accepted within the scientific community and underscores that Planet 9 is a working model, not a conclusion. At the same time, the hypothesis has generated new predictions that are actively being tested. These include the existence of objects on highly inclined or retrograde orbits and the long-term stability of certain orbital groupings. The discovery of such objects adds weight to the idea that an unseen gravitational influence is present. The broader significance of this search lies in what it reveals about scientific method. Planet 9 demonstrates how modern astronomy often proceeds without direct images. Motion, statistics, and simulation combine to infer the presence of unseen objects. This approach is increasingly common in the study of exoplanets, dark matter, and large-scale cosmic structure. The debate surrounding Planet 9 also highlights the importance of skepticism and rigor. Competing explanations are evaluated, biases are scrutinized, and conclusions are withheld until evidence is decisive. This process is slow by design, reflecting the scale of the phenomena involved. Whether Planet 9 is eventually found or ruled out, the effort reshapes understanding of the solar system's outskirts. It reveals a region far more structured and dynamic than previously imagined. It shows that even weak gravitational forces can leave lasting imprints over billions of years. As telescopes grow more powerful and surveys more comprehensive, the question of Planet 9 will move closer to resolution. Discovery would mark a major expansion of the known solar system. Non-detection would force a re-evaluation of assumptions about distant orbital dynamics. Either outcome deepens understanding. If Planet 9 exists, its influence would extend beyond shaping the orbits of distant icy worlds. One of the most significant consequences of a massive, distant planet would be its effect on comets and long-period objects that travel from the outer solar system toward the inner regions. These objects serve as messengers from the outskirts, carrying with them a record of gravitational interactions that have unfolded over billions of years. The outer solar system is surrounded by vast reservoirs of icy bodies. Beyond the Kuiper Belt lies the scattered disk, and farther still, the hypothesized Oort cloud. No, a spherical halo of trillions of comet-like objects extending tens of thousands of astronomical units from the Sun. These regions are loosely bound to the solar system and are sensitive to even small gravitational disturbances. Passing stars, galactic tides, and massive planets can all redirect objects inward or eject them entirely. Planet 9's proposed orbit places it in a position to act as a powerful intermediary between these distant reservoirs and the inner solar system. Its gravity could perturb the orbits of scattered disk objects, altering their trajectories in ways that send some inward while pushing others outward. Over long timescales, this influence could help explain the origin of certain unusual comets and high-inclination objects observed closer to the Sun. Some long-period comets exhibit orbital characteristics that are difficult to reconcile with known planetary influences alone. Their inclinations and perihelion distances suggest that they were redirected from distant regions by an unseen force. Simulations incorporating Planet 9 reproduce similar distributions, suggesting that such a planet could play a role in funneling objects from the outer solar system inward. In particular, Planet 9 may help explain the existence of comets and small bodies on highly inclined or even retrograde orbits. These objects move in directions nearly perpendicular or opposite to the plane of the planets, a configuration that is hard to achieve through interactions with Neptune alone. A distant, inclined planet could gradually torque these orbits, lifting them out of the plane over millions of years. Planet 9's influence would also affect the stability of the scattered disk itself. By shepherding certain populations and destabilizing others, it could help maintain the observed structure of distant object distributions. Without such a planet, some simulations predict that the scattered disk would evolve differently over the age of the solar system. The effect on comets has broader implications. Comet impacts have played a role in Earth's history, delivering water and organic compounds early on and causing mass extinctions later. Understanding what controls the flux of comets into the inner solar system is therefore relevant not only to planetary science, but to the history of life itself. If Planet 9 influences this flux, its existence would have indirect consequences for Earth over geological timescales. The presence of a distant, massive planet would also affect how the solar system interacts with its galactic environment. As the Sun moves through the Milky Way, it experiences tidal forces from the galaxy's gravitational field. Planet 9 could amplify or modulate these effects, altering how objects are transferred between the Oort cloud and interstellar space. This interaction highlights the solar system's permeability. It is not an isolated island, but a system embedded within a galaxy, influenced by external forces. Planet 9, if present, would be a key mediator of this interaction, linking solar and galactic dynamics. The study of cometary orbits provides another way to test the Planet 9 hypothesis. If future observations reveal consistent patterns in the directions and inclinations of long-period comets that match predictions from Planet 9 models, confidence in the hypothesis would grow. Conversely, a mismatch would force revisions or abandonment of the idea. Importantly, these effects unfold slowly. Planet 9 would not cause sudden comet showers or dramatic changes. Its influence would be subtle, cumulative, and spread across millions of years. This slow action aligns with the nature of gravity at extreme distances, where small forces applied over long times dominate outcomes. The idea that a single distant planet could shape such large-scale behavior underscores the sensitivity of the outer solar system. It is a region where order emerges not from strength, but from persistence. Planet 9, if real, Marx, would be an example of how even weak influences can leave lasting imprints when given enough time. These considerations expand the significance of the search. Planet 9 is not just about completing a planetary census. It is about understanding the architecture and evolution of the solar system as a whole, including how it exchanges material with the galaxy. While Planet 9 offers a compelling explanation for many observed features of the distant solar system, it is not the only hypothesis under consideration. Science advances by weighing competing explanations, and the Planet 9 idea must be tested against alternatives that do not require the existence of an unseen planet. These alternative models focus on whether the observed orbital patterns could arise naturally from known forces, observational limitations, or collective behavior among small bodies. One of the most discussed alternatives involves observational bias. The distant solar system is extremely difficult to survey uniformly. Telescopes tend to observe certain regions of the sky more frequently than others, and distant objects are easier to detect when they are closer to the sun. These constraints can produce apparent clustering even if the true distribution is random. Researchers have therefore invested significant effort into modeling the selection effects of surveys to determine how much bias could influence the results. Some studies argue that when biases are fully accounted for, the significance of orbital clustering diminishes. In this view, the apparent alignment of extreme trans-Neptunian objects may reflect where astronomers have looked rather than the presence of a shepherding planet. This interpretation emphasizes caution, noting that the sample size of such distant objects remains small and vulnerable to statistical fluctuation. However, other analyses reach a different conclusion. When realistic survey biases are applied to simulated random populations, the observed degree of alignment still appears unlikely. This disagreement reflects the complexity of the problem. The outer solar system is sparsely populated, faint and slow-moving, making comprehensive sampling extremely challenging. As a result, uncertainty remains an intrinsic part of the debate. Another alternative explanation focuses on collective gravitational effects among small bodies themselves. Rather than a single large planet shaping orbits, the combined mass of many distant objects could, in principle, produce organized behavior over long timescales. This idea suggests that the distant disk may behave more like a weakly self-gravitating system than a collection of independent test particles. While intriguing, this model faces difficulties. The total mass of known distant objects appears too small to generate the observed effects. To reproduce the clustering without Planet 9, the distant disk would need to contain significantly more mass than current observations suggest. This requirement introduces its own uncertainties and raises questions about why such mass has not been detected indirectly. Galactic tides provide another possible influence. The solar system does not exist in isolation, but is embedded within the Milky Way's gravitational field. Over billions of years, the galaxy's tidal forces can alter the orbits of distant objects, particularly those far from the sun. These tides are known to influence the Oort cloud and may play a role in shaping the scattered disk. However, galactic tides act symmetrically and slowly. While they can randomize orbits or inject objects inward, they struggle to produce the specific directional clustering observed among extreme trans-Neptunian objects. Models including galactic tides alone generally fail to replicate the precise alignments that motivated the Planet 9 hypothesis. Passing stars represent yet another factor. During the sun's early history, close stellar encounters were more common. Thus, such encounters could have perturbed distant objects, imprinting long-lasting patterns. Even in the present day, rare stellar flybys can influence the outer solar system. While this mechanism can generate unusual orbits, it tends to produce transient effects rather than stable, long-term clustering. What distinguishes Planet 9 from these alternatives is its ability to explain multiple observations simultaneously. It accounts for orbital clustering, extreme inclinations, long-term stability, and predicted populations of unusual objects within a single framework. Alternative models often address one feature at the expense of others. That said, the Planet 9 hypothesis remains provisional. It must ultimately succeed or fail based on evidence. If future surveys reveal that the clustering dissolves as more objects are discovered, the hypothesis will weaken. If the predicted populations fail to materialize, confidence will drop. Conversely, confirmation of new predictions would strengthen the case. The debate surrounding Planet 9 highlights an important aspect of scientific progress. Competing explanations sharpen analysis, refine data collection, and prevent premature conclusions. Even if Planet 9 is eventually ruled out, the process of testing it will deepen understanding of the outer solar system. This debate also underscores how little is known about the distant reaches beyond Neptune. These regions are not static leftovers. They are dynamic environments shaped by gravity, time, and external influences. Whether organized by a planet or by subtler forces, they hold clues to the solar system's past. As observations improve, the balance between hypotheses will shift. New telescopes, deeper surveys, and longer observational baselines will provide clearer answers. The question of Planet 9 is not whether it is appealing, but whether it is necessary. The question of whether Planet 9 exists may ultimately be decided not by theory, but by technology. Astronomy advances in steps defined by what instruments can see, measure, and track over time. For a hypothesis as challenging as Planet 9, progress depends on surveys capable of observing faint objects across enormous regions of the sky with unprecedented depth and precision. The next generation of observational tools is therefore central to resolving the mystery. One of the most important developments in this effort is the emergence of wide-field time domain surveys. These surveys repeatedly image the same regions of the sky over long periods, allowing astronomers to detect slow-moving objects by comparing subtle changes between observations. This approach is particularly well-suited to finding distant solar system bodies whose motion is imperceptible over short timescales. As survey depth increases, so does sensitivity to faint, cold objects. A planet the size proposed for Planet 9 would not shine brightly, but it would still reflect some sunlight and emit a small amount of infrared radiation. Detecting it requires instruments that can distinguish this faint signal from background stars and galaxies. Advances in image processing, machine learning, and automated detection algorithms have significantly improved this capability. Future surveys are expected to dramatically increase the known population of distant trans-Neptunian objects. This expansion of data will sharpen statistical tests of orbital clustering. If the alignments persist as the sample grows, confidence in a shepherding influence will increase. If they disperse, the case for Planet 9 will weaken. Either outcome represents progress. Beyond optical surveys, infrared astronomy plays a complementary role. Cold objects emit most of their energy at infrared wavelengths, and space-based infrared observatories are less affected by atmospheric interference. While existing infrared surveys have placed constraints on large, warm planets in the outer solar system, future missions with higher sensitivity could probe colder and smaller objects, including those within the expected range for Planet 9. Astrometric measurements also contribute. Precise tracking of the positions of known planets and distant objects can reveal subtle perturbations caused by unseen masses. Although Planet 9's influence on the inner solar system would be extremely weak, cumulative effects over time might become detectable with sufficiently precise data. This approach echoes historical methods used to infer unseen planets through their gravitational effects. Another promising avenue lies in the discovery of predicted populations. Planet 9 models forecast not just one planet, but entire classes of objects with specific orbital properties. Finding these populations would strengthen the hypothesis, even in the absence of direct detection. Failure to find them would challenge the model's assumptions. The resolution of the Planet 9 question will likely be gradual rather than sudden. Unlike Neptune's discovery, which followed a precise prediction, Planet 9 occupies a large and uncertain region of space. Its confirmation may come through a convergence of evidence rather than a single dramatic observation. Importantly, ruling out Planet 9 would be just as significant as discovering it. If exhaustive surveys fail to find such a planet, and the observed orbital patterns are explained through other means, astronomers would gain valuable insight into the dynamics of weakly bound systems. This outcome would refine understanding of how gravity operates at the margins of solar systems. The effort also has broader implications. Techniques developed to search for Planet 9 apply directly to the study of exoplanets, debris disks, and faint structures around other stars. The challenge of detecting distant, cold objects is not unique to our solar system. It reflects a general frontier in astronomy. As technology advances, the boundary between inference and observation shifts. Objects once detectable only through their effects become visible directly. Planet 9 occupies this boundary today. Whether it crosses into confirmed reality depends on how this technological progression unfolds. The search for Planet 9 also highlights the patience required in astronomy. The outer solar system evolves slowly. Objects move on timescales that exceed human lifetimes. Discoveries demand long-term commitment, sustained observation, and careful analysis. As new data arrives, interpretations will be revised. Models will be updated. Hypotheses will be tested and retested. This process is not a sign of uncertainty, but of rigor. It reflects a discipline willing to adapt as evidence demands. The confirmation of Planet 9 would represent one of the most significant discoveries in planetary science in over a century. Not because it adds another name to a list, but because it would fundamentally alter how the solar system is understood. For generations, the solar system has been presented as a largely complete structure, its major components cataloged and mapped. Planet 9 would challenge that assumption, revealing that the architecture of our planetary system is broader, deeper, and more complex than previously believed. One of the most immediate consequences of discovering Planet 9 would be a reassessment of planet formation models. Standard theories describe planets forming within a relatively compact disk of gas and dust surrounding a young star. These models successfully explain the inner planets and the gas giants, but they struggle to account for a massive planet forming or surviving at extreme distances. Planet 9 would force revisions, either by extending formation mechanisms or by emphasizing the role of migration and scattering. If Planet 9 formed closer to the Sun and was later scattered outward, it would provide direct evidence that the early solar system was far more chaotic than its current appearance suggests. Such chaos would imply that planets routinely exchanged energy and angular momentum, sending some worlds inward and others outward. This scenario would align the solar system more closely with observations of exoplanet systems, and many of which display extreme architectures that differ sharply from classical expectations. If Planet 9 were captured from another star, the implications would be equally profound. Capture would mean that planetary systems are not closed systems. but participants in a larger galactic exchange. It would suggest that stars can adopt planets during close encounters, especially in dense stellar environments. This possibility would blur the distinction between native and foreign worlds, implying that the solar system contains material formed beyond the Sun's influence. A captured Planet 9 would also provide insight into the Sun's birth environment. It would support the idea that the Sun formed in a crowded cluster where close encounters were common. Such environments influence the evolution of protoplanetary disks and the survival of distant objects. Planet 9 would become a fossil record of those early conditions. Beyond formation, Planet 9 would reshape understanding of planetary system stability. Its long-term influence on the orbits of distant objects would demonstrate how massive planets can sculpt debris disks over billions of years. This insight would inform studies of other stars surrounded by distant disks, helping astronomers interpret asymmetries and gaps observed around young and mature stars alike. The discovery would also reframe discussions about what constitutes a planet. Planet 9 would occupy a mass range common among exoplanets, but previously absent from the solar system. Its presence would highlight the diversity of planetary types and challenge the notion that the solar system is a typical example. Instead, it would emphasize that our system is one of many possible outcomes. In educational and cultural terms, Planet 9 would alter how the solar system is taught and imagined. Textbooks would expand, diagrams would change. The familiar map ending at Neptune would be extended into deep space. This expansion would remind us that scientific knowledge is provisional, always subject to revision as evidence accumulates. The philosophical implications are equally significant. Planet 9 would underscore that absence of observation does not equate to absence of existence. It would reinforce the idea that inference, when grounded in evidence and theory, is a powerful tool for discovery. This lesson extends beyond astronomy, shaping how knowledge is pursued in fields where direct access is limited. Planet 9 would also influence how future missions are planned. Interest in exploring the outer solar system would intensify, potentially motivating new spacecraft designs capable of traveling farther and operating longer. While a direct mission to Planet 9 would be extraordinarily challenging, its existence would provide a clear scientific target for future generations. The presence of an additional massive planet would also affect long-term dynamical simulations of the solar system. Models of planetary stability, comet flux, and orbital evolution would need revision. These changes would propagate into related fields, influencing understanding of impact rates, debris disk evolution, and planetary habitability. Even the question of how unique the solar system is would be revisited. If Planet 9 exists, the solar system would more closely resemble many exoplanetary systems that contain distant, massive planets on eccentric orbits. This resemblance would suggest that the solar system is not an outlier, but part of a broader continuum of planetary architectures. At the same time, the discovery would raise new questions. Why was Planet 9 not detected earlier? Are there additional distant planets beyond it? How common are such worlds around other stars? Each answer would generate new avenues of inquiry. The absence of Planet 9 would also be informative. If exhaustive searches fail and alternative explanations prevail, the result would refine understanding of how small number statistics and weak forces operate. This outcome would caution against over-interpreting patterns in limited data and reinforce the need for comprehensive surveys. In either case, the Planet 9 hypothesis has already reshaped thinking. It has drawn attention to the outer solar system as an active, structured region rather than a neglected periphery. It has encouraged the development of new methods and collaborations. It has reminded scientists that discovery does not always come from looking brighter, but from thinking deeper. The search for Planet 9 gains additional context when placed alongside discoveries made around other stars. Over the past few decades, astronomers have detected thousands of exoplanets, revealing that planetary systems exhibit a staggering diversity of architectures. Many of these systems contain massive planets on wide, eccentric, or highly inclined orbits, configurations once thought unlikely based on early models of planet formation. This broader cosmic perspective makes the idea of a distant ninth planet in our own solar system less surprising and more plausible. In exoplanetary systems, planets several times the mass of Earth are common. These worlds often occupy regions much farther from their stars than the terrestrial planets do in our solar system. Some are found at distances comparable to or greater than those proposed for Planet 9, though detecting them remains challenging due to their faintness and long orbital periods. Their existence demonstrates that nature readily produces massive planets in diverse environments. Observations of debris disks around other stars further support this view. Many such disks display gaps, warps, and asymmetries that cannot be explained without invoking unseen planets. In these cases, astronomers infer the presence of planets through their gravitational influence on surrounding material, much as Planet 9 is inferred through its effects on distant solar system objects. The method is familiar, even if the scale is different. These comparisons suggest that the solar system may not be as neatly ordered as once believed. Instead, it may share features common to many planetary systems, including distant massive planets that exert subtle but long-lasting influence. If Planet 9 exists, it would place the solar system within a broader pattern observed across the galaxy. The study of exoplanets also informs models of migration and scattering. Many detected planets appear to have moved significantly from their birthplaces, driven by interactions with disks or other planets. This mobility supports scenarios in which Planet 9 formed closer to the Sun and was later displaced. Such processes appear to be common rather than exceptional. Exoplanet research also highlights the limitations of detection methods. Many distant planets remain undetected because current techniques favor large planets close to their stars. The absence of detected analogs to Planet 9 around other stars does not imply rarity. It reflects observational bias. As detection methods improve, more distant and colder planets are likely to be found. The parallels between Planet 9 and exoplanetary discoveries emphasize the importance of inference in astronomy. Whether studying distant stars or our own solar system, astronomers often rely on indirect evidence. Motion, structure, and distribution reveal what light alone cannot. Planet 9 fits squarely within this tradition. This connection also broadens the significance of the Planet 9 hypothesis. It is not merely a local puzzle, but part of a larger effort to understand how planetary systems form and evolve across the galaxy. Discovering or ruling out Planet 9 would refine models applied far beyond the Sun. At the same time, the solar system offers advantages unavailable in exoplanet studies. Distant objects within our system can be observed in far greater detail than exoplanets. Their orbits can be measured precisely, and their long-term evolution modeled with confidence. This makes the solar system a laboratory for testing ideas relevant to planetary systems everywhere. The interplay between local and distant observations strengthens the scientific process. Insights gained from exoplanets inform interpretations of solar system data and vice versa. Planet 9 sits at this intersection, linking local dynamics with galactic trends. As research continues, the boundary between planetary science and stellar astronomy becomes increasingly blurred. Planet 9 exemplifies this convergence. Its potential existence connects the behavior of small icy bodies, the dynamics of massive planets, and the broader patterns observed around other stars. Although Planet 9 is proposed to reside far beyond the known planets, its influence would not be confined entirely to the distant outskirts. Over the immense timescales of the solar system's existence, even a weak gravitational presence can leave subtle but measurable effects closer to the Sun. Understanding whether Planet 9 could influence the known planets requires careful analysis of long-term dynamics rather than immediate motion. The inner solar system is dominated by the gravitational influence of Jupiter and Saturn. These gas giants shape the architecture of planetary orbits, asteroid belts, and comet pathways. Any distant planet would be vastly weaker by comparison. However, gravity operates cumulatively. Over billions of years, persistent torques can slowly alter orientations and angular momentum distributions across the system. One of the most intriguing connections between Planet 9 and the known planets involves the tilt of the Sun itself. The Sun's rotation axis is inclined by about 6 degrees relative to the average orbital plane of the planets. This misalignment has long puzzled astronomers because standard models of solar system formation predict that the Sun and planets should be closely aligned, having formed from the same rotating disk of gas and dust. Simulations show that a distant, inclined, massive planet could slowly torque the planetary system over time, shifting the orientation of the planetary plane relative to the Sun's equator. This effect would occur gradually, accumulating over billions of years. Importantly, it would not disrupt planetary orbits or cause instability. Instead, it would gently tilt the entire system as a coherent structure. This explanation does not require Planet 9 to exert strong forces on individual planets. It relies on long-term averaging, where small gravitational influences compound steadily. The resulting tilt matches the observed value remarkably well in some models, adding another line of circumstantial evidence in favor of Planet 9's existence. Beyond the Sun's tilt, Planet 9 could also influence the distribution of angular momentum in the outer planets. While the effects would be subtle, precise simulations suggest that small deviations in orbital inclination and node alignment could arise over time. These deviations are difficult to measure directly, but they provide constraints on how massive and inclined Planet 9 could be without destabilizing the system. Importantly, no observed features of the known planets contradict the Planet 9 hypothesis. The orbits of Mercury through Neptune are stable and well explained by existing models. Planet 9, if present, must operate within strict limits to preserve this stability. Current simulations show that it can do so, provided it occupies a distant, elongated orbit with the right orientation. The absence of dramatic effects on the inner solar system is itself informative. It constrains Planet 9's mass and distance, ruling out more massive or closer configurations. This refinement illustrates how non-detections play an essential role in shaping scientific understanding. Planet 9's influence would also interact with secular resonances, slow oscillations in orbital elements that occur due to gravitational coupling. These resonances operate over long timescales and can transmit influence across large distances. Through such mechanisms, Planet 9 could affect the orientation of distant orbits without directly perturbing the inner planets. This layered structure of influence reflects the hierarchical nature of the solar system. Strong forces dominate nearby regions, while weaker forces shape distant ones. Planet 9 would occupy the outermost tier of this hierarchy, exerting control primarily over the solar system's boundary rather than its core. Understanding these interactions requires precise numerical modeling that spans billions of years. Such models must account for the combined effects of all major planets, galactic tides, and potential distant companions. The fact that Planet 9 can be incorporated into these models without causing instability strengthens its plausibility. At the same time, but this subtlety explains why Planet 9 escaped notice for so long. Its presence would not announce itself through dramatic perturbations or obvious anomalies. Instead, it would reveal itself through small but persistent deviations, visible only through careful statistical analysis. The possibility that a distant planet could shape the solar system so gently, yet so persistently, challenges intuitive notions of causality. It demonstrates that influence does not require proximity or strength, only time. In a system billions of years old, patience is power. Defining the edge of the solar system is far more complex than drawing a line beyond the last known planet. The solar system does not end abruptly. It fades gradually into interstellar space through regions where the sun's gravitational influence weakens, but never entirely disappears. So Planet 9, if it exists, would occupy a critical position in this transition zone, helping define where the solar system truly gives way to the galaxy. Traditionally, the solar system has been described as extending out to the Kuiper Belt and farther still, to the Oort cloud. The Kuiper Belt marks the region of icy remnants beyond Neptune, while the Oort cloud is thought to form a vast, spherical shell of objects extending tens of thousands of astronomical units from the Sun. These regions are bound to the Sun, but are extremely sensitive to external influences such as passing stars and galactic tides. Planet 9's proposed orbit lies between these two conceptual boundaries. It would exist beyond the classical Kuiper Belt, but well inside the outer reaches of the Oort cloud. In this intermediate region, gravity from the Sun, the planets, and the galaxy all compete. A massive planet in this zone would act as an organizer, shaping how material transitions from being tightly bound to loosely attached. In this sense, Planet 9 would function as a gatekeeper of the outer solar system. Its gravity could regulate which objects remain bound and which are ejected into interstellar space. Over billions of years, this influence would contribute to sculpting the distribution of distant objects, reinforcing certain orbital pathways while destabilizing others. The concept of a boundary shaped by gravity rather than distance is central here. The solar system's edge is not where objects stop existing, but where solar gravity loses dominance. Planet 9 would extend that dominance in certain directions while weakening it in others, creating an asymmetric boundary rather than a uniform shell. This asymmetry may already be visible. Observations suggest that the distribution of distant objects is not uniform in all directions. Certain regions appear more populated or more dynamically structured than others. A distant planet on an inclined orbit could naturally create such asymmetry by preferentially influencing objects along its orbital path. The interaction between Planet 9 and galactic tides is particularly important. Galactic tides slowly stretch and compress the solar system's outer regions as the Sun orbits the Milky Way. Planet 9 could amplify or counteract these tides locally, altering how objects migrate between the scattered disk and the Oort cloud. This interaction would further blur the distinction between solar and galactic influence. Understanding this boundary region has implications beyond planetary science. It informs models of how solar systems exchange material with the galaxy. Interstellar objects, such as those detected passing through the solar system, may originate from similar boundary zones around other stars. Planet 9 would therefore be part of a broader story about how systems lose and gain material over time. The presence of a distant massive planet would also affect the stability of the Oort cloud's inner regions. While Planet 9 would not dominate the entire cloud, its gravity could influence the orbits of objects near its aphelion. This influence could shape the long-term structure of the cloud, contributing to anisotropies that persist across cosmic time. These effects highlight that the solar system is not a static structure frozen since formation. It is a dynamic system continually reshaped by internal and external forces. Planet 9, if present, would be an active participant in this evolution, guiding the slow redistribution of mass at the system's edge. The idea that a single planet could influence the solar system's boundary challenges traditional views of planetary importance. It suggests that planets need not be close or bright to be significant. Influence is measured not only in immediate effect, but in cumulative consequence. As models become more refined, researchers are beginning to treat the outer solar system as a continuum rather than a set of discrete regions. Kuiper Belt, scattered disk, and Oort cloud are seen as connected phases in a gradient of gravitational binding. Planet 9 fits naturally into this continuum, occupying a region where organization gives way to dispersion. This perspective reframes the Planet 9 hypothesis as part of a larger effort to understand solar system architecture as a whole. It is not simply about adding a planet, but about recognizing how structure emerges at the margins. When considering the long-term future of the solar system, Planet 9 becomes more than a present-day mystery. It becomes a factor in how the system will evolve over billions of years. The solar system is not static. Its structure changes slowly but continuously as gravitational interactions accumulate, stars pass nearby, and the sun itself evolves. A distant massive planet would influence this future in subtle yet persistent ways. Over the next several billion years, the sun will gradually increase in luminosity as it ages. While this change will dramatically affect the inner planets, it will have little direct impact on the outer solar system. Planet 9, if it exists, would remain largely unaffected by solar evolution in terms of temperature and illumination. However, the changing mass distribution of the solar system, particularly if the sun loses mass during later evolutionary stages, would alter gravitational balances throughout the system. As the sun eventually enters its red giant phase, it will lose a significant fraction of its mass through stellar winds. This mass loss will weaken the sun's gravitational hold, causing planetary orbits to expand. And the known planets will drift outward slightly, and distant objects will be affected even more strongly. Planet 9's orbit would expand as well, potentially moving it farther into the transitional zone between the solar system and interstellar space. In this future scenario, Planet 9 could play a stabilizing role for some distant objects while destabilizing others. As the sun's grip weakens, Planet 9's relative influence on nearby bodies could increase. Objects that were once marginally bound might become unbound, escaping into interstellar space. Others might be redirected inward or trapped into new resonant configurations. The interaction between Planet 9 and passing stars becomes more important on long timescales. Stellar encounters, while rare on human timescales, are inevitable over billions of years. A massive planet in the outer solar system would alter how these encounters affect distant objects. It could shield certain regions by absorbing or redirecting perturbations, while amplifying disturbances in others. These processes contribute to the gradual erosion of the solar system's outer reservoirs. The scattered disk and inner Oort cloud are expected to lose material over time through a combination of planetary interactions and galactic tides. Planet 9 would influence the rate and direction of this loss, shaping how the solar system sheds mass into the galaxy. This slow leakage of material has implications for the distribution of interstellar objects. Objects ejected from our solar system may wander the galaxy, potentially passing through other planetary systems. In this way, Planet 9 would indirectly participate in a galactic exchange of material, contributing to the population of rogue objects drifting between stars. The long-term stability of Planet 9 itself also depends on galactic conditions. While its orbit would be stable on timescales comparable to the age of the solar system, extreme future events such as close stellar encounters or changes in the galactic environment could alter its path. In some distant future, Planet 9 could be ejected or captured by another star, just as it may have been captured itself. These possibilities underscore that planetary systems are not permanent structures. They evolve, interact, and sometimes dissolve. Planet 9 would be part of this ongoing transformation, a participant in the slow reconfiguration of the Sun's gravitational domain. Considering these futures places Planet 9 in a broader cosmic context, its existence would not only explain present-day observations, but also inform predictions about the solar system's distant fate. It would demonstrate how even remote planets can influence outcomes across immense spans of time. This perspective also highlights the importance of studying the outer solar system now. The current configuration preserves a record of early conditions and long-term evolution. Planet 9, if real, would be both a relic of the past and an agent of future change. The idea of Planet 9 fits into a long historical pattern in astronomy, one in which unseen worlds are proposed to explain observed motion. Long before telescopes could resolve distant planets directly, astronomers learned to read gravity as a form of language. And deviations in motion became messages, pointing toward the presence of objects hidden from view. Planet 9 is the latest expression of this tradition, linking modern computational astronomy with centuries-old methods of inference. In the early 19th century, irregularities in Uranus's orbit led astronomers to suspect the presence of another planet. Mathematical predictions narrowed the search, and Neptune was discovered close to its predicted position. This success established a powerful precedent. It demonstrated that gravity could reveal what light had not yet shown. Planet 9 echoes this moment, though under far more challenging conditions. The comparison also reveals important differences. Neptune's influence on Uranus was strong and immediate, producing clear discrepancies in orbital motion. Planet 9's influence is weaker and spread across a population of small objects rather than a single planet. The signal is statistical rather than direct. This distinction reflects how astronomy has evolved from individual anomalies to patterns discerned through large data sets. The history of planetary discovery also includes cautionary tales. The hypothetical planet Vulcan was proposed to explain anomalies in Mercury's orbit. Vulcan was never found. The anomaly was later explained by a deeper understanding of gravity through general relativity. This episode serves as a reminder that unseen planets are not the only possible explanation for unexpected motion. Sometimes the laws themselves must be revised. This historical context shapes how scientists approach Planet 9. The hypothesis is treated with interest but also restraint. It is tested rigorously against alternatives. Its predictions are examined critically. Its failure would not represent defeat, but progress, just as the abandonment of Vulcan led to a more complete theory of gravity. Public fascination with Planet 9 reflects a deeper cultural theme. The idea that our cosmic neighborhood may still hold undiscovered worlds challenges the perception of completeness. It suggests that exploration is not finished, even close to home. This resonates with a long human tradition of pushing boundaries and revising maps. Planet 9 also occupies a unique place in planetary naming and identity. It is not yet a planet in the formal sense. It has no official designation, no confirmed orbit, no direct observation. Its name functions as a placeholder, a linguistic acknowledgement of uncertainty. This provisional status reflects a scientific culture that distinguishes between hypothesis and discovery. The debate surrounding Planet 9 has also influenced how astronomical data is collected and shared. Large collaborations, open datasets, and independent analyses have become central to the process. This openness allows competing interpretations to be evaluated transparently, strengthening confidence in eventual conclusions. Media coverage of Planet 9 often emphasizes mystery and speculation. But within the scientific community, the focus remains on method. The question is not whether Planet 9 is exciting, but whether it is necessary. Does it provide the simplest and most consistent explanation for the data, or do alternatives suffice? This emphasis reflects a disciplined approach to discovery. The Planet 9 hypothesis has also shaped how scientists think about absence. Traditionally, astronomy focused on what could be seen. Increasingly, it focuses on what must exist to account for observed structure. Dark matter, dark energy, and unseen planets all fall into this category. Planet 9 is part of a broader shift toward inference-based cosmology. This shift does not diminish the importance of observation. On the contrary, it places greater demands on data quality and interpretation. Observations must be precise enough to support or refute subtle effects. Planet 9 challenges astronomers to extract meaning from faint signals at the edge of detectability. The cultural impact of Planet 9 extends beyond science. It influences how the solar system is imagined in art, literature, and education. The possibility of a hidden world lurking in deep space captures imagination, blending scientific rigor with a sense of wonder. Yet the enduring appeal of Planet 9 lies not in mystery alone, but in what it represents about knowledge. It shows that understanding advances through questioning assumptions, revisiting conclusions, and remaining open to revision. The solar system, once thought complete, becomes a dynamic hypothesis rather than a closed case. As this exploration continues, Planet 9 remains unresolved. Its status is neither confirmed nor dismissed. It exists in a productive state of uncertainty, driving observation, debate, and discovery. At its core, the Planet 9 hypothesis offers a lesson in how science operates at the edge of knowledge. It demonstrates that discovery is not always a sudden revelation, but often a gradual process shaped by uncertainty, probability, and revision. Planet 9 exists not as an object of belief, but as a working explanation, one that stands only as long as it continues to account for observations better than competing ideas. This distinction is essential. Scientific hypotheses are tools, not conclusions. They organize information, generate predictions, and guide observation. Planet 9 functions in this role by providing a coherent framework for understanding multiple anomalies in the outer solar system. Its value lies not in its certainty, but in its usefulness. The hypothesis also illustrates the importance of scale in scientific reasoning. At extreme distances, where forces are weak and motion is slow, effects become subtle. Detecting order in such environments requires large data sets, or long-time baselines, and careful statistical analysis. Planet 9 challenges astronomers to distinguish genuine structure from coincidence in a realm where data is sparse and uncertainty unavoidable. This challenge highlights the role of probability in modern astronomy. Unlike laboratory experiments, astronomical phenomena cannot be repeated or controlled. Scientists must work with what the universe provides, interpreting patterns across incomplete samples. Planet 9's proposed existence is supported not by direct measurement, but by the improbability of observed patterns arising by chance. Yet, probability alone is not proof. Competing models remind researchers that statistical significance depends on assumptions about data completeness and bias. This tension drives refinement, encouraging better surveys, improved modeling, and more cautious interpretation. In this way, uncertainty becomes productive rather than paralyzing. Planet 9 also reveals how theories evolve alongside technology. What was once undetectable becomes accessible as instruments improve. Conversely, hypotheses must adapt as new data narrows possibilities. The gradual constraining of Planet 9's possible properties reflects this dynamic interplay between idea and observation. The hypothesis further underscores the interconnectedness of scientific disciplines. Understanding Planet 9 requires celestial mechanics, statistical analysis, computational modeling, and observational astronomy. It also draws on insights from exoplanet studies, stellar dynamics, and galactic structure. This interdisciplinary approach reflects the complexity of modern scientific questions. Another lesson lies in the humility embedded within scientific practice. Despite its appeal, Planet 9 is not assumed to exist. Researchers remain open to the possibility that the hypothesis will fail. This openness is not weakness, but strength. It ensures that conclusions remain provisional and responsive to evidence. Planet 9 also highlights the difference between explanation and existence. A model can explain data effectively without corresponding to a physical object. The history of science contains many such examples. Recognizing this distinction helps maintain rigor and prevents premature claims. At the same time, the hypothesis demonstrates the power of inference. Even without direct observation, gravity leaves traces. Motion encodes history. Patterns reveal influence. Planet 9 exemplifies how unseen causes can be reconstructed through their effects, a principle that extends across physics and cosmology. The broader implication is that knowledge is often indirect. Much of what is known about the universe comes from interpreting signals rather than observing sources directly. Planet 9 fits comfortably within this epistemological framework, alongside dark matter, gravitational waves before detection, and distant exoplanets inferred through stellar motion. As the debate continues, Planet 9 serves as a reminder that uncertainty does not imply ignorance. It reflects engagement with complexity. It marks the boundary between what is known and what is being explored. This boundary is where science thrives. It is where questions are refined, methods improved, and understanding deepened. Whether Planet 9 is eventually confirmed or discarded, the process of investigating it will leave astronomy more robust than before. Whether Planet 9 is ultimately confirmed or ruled out, its influence on how the solar system is perceived is already profound. The hypothesis has shifted attention outward, toward regions once considered peripheral and unimportant. It has reframed the outer solar system as an active, structured environment rather than a static graveyard of debris. This change in perspective endures regardless of the hypothesis's final outcome. For much of the 20th century, the solar system was portrayed as orderly and complete. The planets formed a neat sequence, and beyond them lay only remnants. Discoveries of the Kuiper Belt and scattered disk disrupted this simplicity, revealing complexity at the margins. Planet 9 extends this disruption further, suggesting that even large, dominant bodies may exist far beyond traditional boundaries. This expanded view aligns with a broader trend in astronomy. As observations deepen, systems once thought simple reveal hidden layers. Galaxies show unseen mass. Stars host unexpected companions. Planetary systems display architectures that defy early models. Planet 9 fits naturally into this pattern, reinforcing the idea that cosmic systems are richer than initial observations suggest. The hypothesis also reshapes how scale is understood. distances that once seemed prohibitively large are now treated as meaningful domains of structure. Timeframes spanning billions of years are recognized as active periods during which subtle forces accumulate. Planet 9 embodies this recognition, operating not through dramatic events, but through patience. This emphasis on slow influence offers a counterpoint to more violent cosmic narratives. It highlights that change does not always require catastrophe. Sometimes it emerges from steady pressure applied consistently over immense time. This principle applies across physics, from orbital dynamics to geological processes, and Planet 9 provides a clear astronomical example. The cultural resonance of Planet 9 stems partly from this quiet power. It is not a blazing world or disruptive intruder. It is a silent participant, shaping motion without being seen. This subtlety distinguishes it from more sensational discoveries and underscores the sophistication of modern astronomy. Planet 9 also prompts reflection on the limits of exploration. Even in an age of space probes and powerful telescopes, some regions remain beyond direct reach. The outer solar system challenges assumptions about accessibility and reminds us that discovery often begins with inference rather than observation. This realization does not diminish the value of exploration. Instead, it expands its scope. Exploration becomes not only a matter of travel, but of analysis, simulation, and interpretation. Planet 9 exemplifies this expanded definition, where understanding advances through modeling as much as measurement. The hypothesis also illustrates the cumulative nature of knowledge. Planet 9 was not proposed based on a single observation, but on patterns emerging across decades of data collection. Each distant object discovered added context. Each simulation refined interpretation. This accumulation reflects the collaborative, incremental character of science. In this sense, Planet 9 is already a discovery of sorts. It has revealed patterns that were previously unrecognized. It has identified gaps in understanding. It has motivated new surveys and analytical methods. These contributions persist regardless of the planet's physical existence. The broader lesson is that science advances by confronting uncertainty rather than avoiding it. Planet 9 occupies a space where evidence is suggestive but incomplete. Engaging with this uncertainty drives progress, encouraging refinement of theory and observation alike. As the investigation continues, Planet 9 remains a focal point for curiosity and debate, and it draws together multiple threads of astronomy, from celestial mechanics to galactic dynamics. It challenges assumptions while remaining grounded in evidence. In the next part, we will move closer to conclusion by considering how Planet 9 reflects humanity's ongoing relationship with the unknown. We will examine why mysteries like this persist, what they reveal about scientific inquiry, and how they shape our understanding of the universe as an evolving system rather than a finished map. Planet 9 occupies a distinctive place in humanity's long relationship with the unknown. Throughout history, the edges of maps have carried both danger and possibility. As exploration progressed, coastlines sharpened, continents took shape, and blank spaces receded. Yet even as physical maps filled in, conceptual frontiers remained. Planet 9 exists within one of these frontiers, where certainty fades not because of ignorance, but because the universe itself is subtle. This subtlety challenges expectations shaped by earlier eras of discovery. The planets most familiar to humanity announce themselves clearly. They shine, move noticeably against the stars, and invite direct observation. Planet 9 does none of these things. Its proposed existence emerges quietly, through patterns discerned only after years of data accumulation and analysis. This quietness reflects a broader shift in scientific discovery, from dramatic sightings to patient inference. The persistence of such mysteries reveals something essential about scientific inquiry. Knowledge does not progress toward completion. Each discovery opens new questions. Each answer exposes deeper layers. Planet 9, whether real or not, represents this dynamic process. It reminds us that understanding is provisional, shaped by current tools and concepts. The hypothesis also illustrates how scientific imagination operates within constraints. Planet 9 is not a free-floating speculation. It is bounded by physics, informed by data, and tested against alternatives. Its imagined properties arise from necessity rather than creativity. In this way, it exemplifies disciplined imagination, where ideas are shaped by what must be true rather than what is merely possible. This discipline distinguishes scientific mystery from myth. Planet 9 is not mysterious because it defies explanation, but because explanation remains incomplete. Its mystery invites investigation rather than reverence. It motivates refinement rather than belief. The continued interest in Planet 9 also reflects a psychological dimension of exploration. Humans are drawn to the idea that something familiar may still contain surprises. The solar system, often presented as a closed chapter, becomes once again a site of potential discovery. This reawakening of curiosity reinforces the idea that exploration is ongoing, even in well-studied domains. Planet 9 further emphasizes the role of uncertainty as a constructive force. Rather than undermining confidence, uncertainty here drives methodological rigor. It encourages skepticism, cross-checking, and collaboration. Competing interpretations sharpen analysis. Disagreement becomes a tool rather than an obstacle. This dynamic is visible in the way the Planet 9 hypothesis has evolved. Initial proposals have been refined as new data emerged, and mass estimates narrowed, orbital parameters adjusted, predictions updated. This evolution demonstrates responsiveness to evidence, a hallmark of robust scientific practice. The hypothesis also highlights the importance of time in scientific understanding. The outer solar system evolves slowly, and so does knowledge of it. Detecting patterns requires patience across years and decades. This timescale contrasts with the immediacy often associated with discovery, reminding us that some truths reveal themselves only gradually. In this context, Planet 9 serves as a reminder that not all exploration involves travel. Much of modern discovery occurs through interpretation of data collected remotely. Telescopes, simulations, and statistical models extend perception beyond physical reach. Planet 9 exemplifies this extension, existing at the limit of what can be inferred from afar. The discussion surrounding Planet 9 also illustrates how scientific narratives are constructed. Data alone does not tell a story. Interpretation organizes facts into coherent explanations. Planet 9 provides a narrative framework that connects disparate observations into a unified picture. Whether this picture corresponds to reality remains to be determined, but its coherence makes it compelling. At the same time, scientists remain aware that coherence is not confirmation. The history of science contains many elegant explanations later replaced by better ones. This awareness tempers enthusiasm with caution, maintaining balance between curiosity and restraint. Planet 9 thus stands as both possibility and test. It tests observational capability, theoretical models, and interpretive frameworks. It also tests patience, humility, and openness to revision. In this way, it reflects the values underlying scientific inquiry. As this exploration continues toward its conclusion, Planet 9 remains unresolved. Its status is neither affirmed nor denied. Instead, it occupies a productive space of investigation, where questions guide effort and uncertainty fuels progress. When the Planet 9 hypothesis is viewed as a whole, it becomes clear that its importance extends beyond the question of whether a single distant planet exists. It represents a case study in how modern science confronts incomplete information. Rather than waiting for certainty, researchers work within uncertainty, constructing explanations that remain flexible, testable, and responsive to new evidence. Planet 9 embodies this approach, our standing as a provisional answer shaped by what is known and constrained by what is not. The hypothesis also illustrates how structure can emerge from apparent randomness. For many years, the outer solar system was assumed to be chaotic, its distant objects scattered without order. The recognition of orbital clustering challenged that assumption, suggesting that even in regions governed by weak forces, patterns can persist. Whether these patterns arise from a hidden planet or another mechanism, their existence signals that the outer solar system retains memory of its past. This idea of memory is central. Orbits preserve information about interactions that occurred millions or billions of years ago. Unlike surfaces that erode or atmospheres that change, orbital configurations can remain stable for immense spans of time. Planet 9, but if real, would be both a cause and a consequence of this memory, shaping it while being revealed by it. The investigation also underscores the role of computation in contemporary astronomy. Simulations are not mere illustrations. They are essential tools that allow scientists to explore scenarios impossible to test experimentally. By adjusting parameters and observing outcomes, researchers identify which conditions produce observed structures. Planet 9 emerged from this computational exploration, highlighting how theory and data intertwine. These simulations also reveal the fragility of explanations. Small changes in assumptions can lead to different outcomes. This sensitivity reinforces the need for careful validation and cross-checking. It also explains why consensus develops slowly. Confidence grows not from a single result, but from repeated convergence across independent approaches. Planet 9 further demonstrates the value of negative results. Each region of sky surveyed without detection refines the hypothesis. Each alternative model tested and found wanting clarifies which explanations remain viable. In science, absence of evidence can still inform understanding when interpreted correctly. The broader implication is that knowledge advances through constraint as much as discovery. Planet 9's possible properties have narrowed over time, even without direct observation. This narrowing represents progress. It reflects a growing understanding of what the outer solar system can and cannot contain. The hypothesis also highlights the collaborative nature of modern science. No single observation or researcher defines the outcome. A progress emerges from the collective effort of observers, theorists, and analysts across institutions and continents. Planet 9 is not owned by any individual. It is a shared problem approached from multiple perspectives. This collaboration extends to the public realm. Interest in Planet 9 has drawn attention to the outer solar system, encouraging engagement with astronomy beyond familiar topics. While popular narratives may emphasize mystery, they also provide an entry point into deeper understanding of how science operates. At the same time, Planet 9 challenges the tendency to seek closure. It resists definitive resolution, at least for now. This resistance serves as a reminder that not all questions yield quick answers. Some remain open, guiding inquiry across generations. The solar system, often presented as a finished structure, emerges instead as an evolving system whose full inventory and dynamics are still being revealed. Planet 9 reinforces this perspective, showing that even familiar territory can contain surprises when examined with new tools and ideas. As attention turns toward synthesis, the Planet 9 hypothesis can be seen as part of a continuum rather than an isolated case. It echoes earlier discoveries and anticipates future ones. It bridges historical methods of inference with modern computational analysis. It connects local observations with broader galactic context. In this way, Planet 9 becomes symbolic of a deeper truth. The universe is not fully mapped. Understanding is provisional. Exploration continues not because ignorance persists, but because complexity is intrinsic. And as we approach the final chapters of this exploration, the focus shifts from specific mechanisms to overarching meaning. Planet 9 invites reflection on what it means to know, to infer, and to remain open to revision. It challenges static views of knowledge and encourages ongoing inquiry. The future of the Planet 9 question is inseparable from the future of astronomy itself. As observational capabilities expand, the line between what can be inferred and what can be directly detected continues to shift. Technologies now coming online are designed not only to see farther, but to see differently, capturing faint motion, subtle brightness changes, and long-term patterns that were previously inaccessible. Planet 9 stands at the threshold of this transformation. Next-generation sky surveys will repeatedly image enormous portions of the sky with unprecedented depth and consistency. This repeated coverage is essential for detecting distant solar system objects whose motion unfolds slowly over time. Unlike traditional surveys that capture static snapshots, these projects build dynamic maps, allowing astronomers to identify objects based on movement rather than brightness alone. A distant planet moving against the background of stars becomes detectable not because it shines, but because it shifts. These surveys will dramatically increase the number of known trans-Neptunian objects, providing a much larger data set with which to test orbital clustering. As sample sizes grow, statistical uncertainties shrink. Mirror patterns that once seemed tentative may either strengthen into robust signals or dissolve into randomness. Planet 9's fate depends heavily on this expansion of data. Improved infrared observations will also play a role. Cold objects emit most of their energy at long wavelengths, and advances in infrared sensitivity may reveal faint heat signatures from distant worlds. While Planet 9 would be extremely cold, its residual internal heat could still produce detectable emission under the right conditions. Even a non-detection would further constrain its possible size and temperature. Astrometry offers another avenue of progress. By measuring positions of objects with extraordinary precision over long timescales, astronomers can detect minute gravitational influences. And this technique has already revolutionized stellar astronomy and holds potential for revealing subtle perturbations in the outer solar system. While challenging, such measurements could provide indirect confirmation or rejection of a distant massive planet. The resolution of the Planet 9 hypothesis will likely emerge from convergence rather than a single breakthrough. Independent lines of evidence, each incomplete on its own, may align to support or refute the idea. This convergence reflects the nature of complex scientific questions, where certainty is built gradually through accumulation rather than revelation. Beyond Planet 9 itself, the methods developed to search for it will have lasting impact. They will be applied to other hidden structures, from distant debris disks to faint companions around stars. The techniques of inference, pattern recognition, and long-term monitoring refined through this search will shape future discovery. The broader implication is that astronomy is increasingly becoming a science of systems rather than objects. Planet 9 is not sought in isolation, but as part of an interconnected network of bodies whose collective behavior reveals underlying structure. This system's perspective aligns with trends across science, emphasizing relationships over individual components. The search also reinforces the importance of patience in discovery. The outer solar system operates on timescales that exceed human experience. Detecting change requires sustained commitment across decades. Planet 9 may not reveal itself quickly, but the effort itself advances understanding regardless of outcome. One, as humanity continues to refine its tools, the boundaries of the solar system will come into sharper focus. Whether Planet 9 emerges as a confirmed world or fades as an explanatory placeholder, the process of investigation will leave a more detailed map of the Sun's gravitational domain. In this way, Planet 9 serves as a bridge between present knowledge and future capability. It marks a question that current tools can approach but not yet fully answer. It motivates development of methods that will address similar questions elsewhere in the universe. As we near the end of this exploration, attention turns toward reflection. What does the Planet 9 hypothesis ultimately reveal about how knowledge grows, how uncertainty is managed, and how exploration persists even when direct access is limited? Planet 9 ultimately represents more than a potential addition to the solar system. It represents a moment in the ongoing dialogue between observation and interpretation, between what is seen and what must be inferred. Its significance lies not only in whether it exists, but in how its possibility reshapes understanding of the solar system as a living, evolving structure rather than a completed map. The enduring appeal of Planet 9 arises from its position at the boundary of certainty. It occupies a region where evidence is suggestive but incomplete, where patterns invite explanation but resist closure. This tension is not a flaw in the scientific process. It is one of its defining features. Science advances not by eliminating uncertainty all at once, but by learning to work productively within it. Onto Planet 9 also reveals how much of the universe remains beyond direct reach. Even within the solar system, distances are vast, light is scarce, and motion unfolds slowly. Discovery in such environments requires methods that prioritize inference, persistence, and statistical reasoning over immediacy. The hypothesis demonstrates that understanding does not depend solely on seeing, but on recognizing the consequences of unseen influence. The possibility of a distant planet also reframes the concept of familiarity. The solar system is often presented as humanity's cosmic home, a region fully charted and understood. Planet 9 challenges this narrative by suggesting that even our nearest astronomical environment may contain elements still hidden. This realization encourages humility, reminding us that knowledge remains provisional even in domains long studied. From a scientific standpoint, Planet 9 has already proven valuable. It has sharpened attention on the outer solar system, motivated new surveys, and refined models of long-term gravitational dynamics. It has prompted re-examination of assumptions about randomness and structure at great distances. These contributions persist regardless of the hypothesis's eventual outcome. The debate also highlights the importance of negative space in discovery. Absence itself becomes data. Regions of sky searched without result constrain possibilities. Patterns that weaken under expanded datasets refine interpretation. Planet 9 exemplifies how scientific understanding grows through elimination as much as confirmation. This process mirrors broader patterns in astronomy. A dark matter was inferred long before it was detected directly and remains unseen even now. Gravitational waves were predicted decades before their observation. In each case, the universe revealed itself indirectly first, through motion and structure, rather than direct image. Planet 9 fits within this tradition of discovery through consequence. At the same time, history cautions against certainty without confirmation. The example of Vulcan reminds us that unseen planets are not the only explanation for anomalous motion. Deeper understanding of physical law can resolve discrepancies without adding new objects. Planet 9 remains subject to this possibility, and its continued evaluation reflects this awareness. What distinguishes the Planet 9 hypothesis is its explanatory reach. It connects multiple observations across different populations of objects and timescales. This coherence gives it strength, but not immunity. As new data arrives, coherence must persist or give way. Beyond technical considerations, Planet 9 touches on a more philosophical dimension of exploration. It raises questions about what it means to know a place. Is a region understood when it is mapped visually or when its behavior is explained? Planet 9 suggests that understanding arises from recognizing relationships rather than cataloging appearances. This relational understanding aligns with modern views of the universe as a network of interactions. Objects matter not only for what they are, but for what they do. Planet 9, if real, would be defined primarily by influence rather than visibility. Even if unreal, the idea reinforces the importance of interaction as a source of knowledge. The hypothesis also underscores the role of patience in science. Answers to questions at the edge of detectability do not arrive quickly. They require sustained observation, careful analysis, and willingness to revise conclusions. Planet 9 is a reminder that some discoveries unfold on timescales that challenge human expectations. As this exploration approaches its conclusion, Planet 9 remains unresolved. Its ambiguity is not a failure, but a reflection of the scale and subtlety of the phenomena involved. It stands as an invitation rather than a verdict, pointing toward future investigation rather than finality. The story of Planet 9 ultimately resolves not into an answer, but into a deeper understanding of how exploration works when certainty is distant and evidence unfolds slowly. Whether the planet exists as a physical world orbiting far beyond Neptune, or remains an elegant explanation that will one day be replaced, its role in scientific thought is already secure. It has changed how the outer solar system is perceived, transforming it from a neglected margin into an active frontier. Planet 9 reminds us that the universe does not reveal itself all at once. Some truths emerge through brightness and immediacy. Others appear only through accumulation, patience, and inference. At extreme distances, gravity speaks more clearly than light, and motion becomes a language that must be translated carefully. Planet 9 exists within that language, written into the paths of distant objects and the structure of space at the solar system's edge. This realization reframes discovery itself. Discovery is not always the moment of seeing, but the moment of understanding. It can arrive through recognizing patterns, resolving contradictions, and refining explanations. In this sense, Planet 9 has already been discovered as an idea, even if its physical confirmation remains uncertain. The hypothesis also underscores the adaptability of scientific knowledge. The solar system, once thought complete, has been repeatedly revised. New regions were added, new categories introduced, definitions reconsidered. Planet 9 continues this tradition, reinforcing that scientific maps are provisional, shaped by evidence rather than expectation. There is also a lesson here about scale. Human intuition is shaped by environments where forces act quickly and distances are modest. The outer solar system operates under different rules, where weak forces dominate through endurance rather than strength. Planet 9 embodies this principle, exerting influence not through immediacy, but through time. This slow influence reflects a broader truth about the universe. Change does not always arrive through dramatic events. Often it emerges through persistent pressure applied across vast durations. Orbits shift, structures form, patterns endure. Planet 9, real or not, illustrates how subtle forces can organize complexity when given enough time. The hypothesis further highlights the value of uncertainty. Rather than representing ignorance, uncertainty here signals active engagement with evidence at its limits, or it motivates improved observation, sharper analysis, and deeper questioning. Planet 9 occupies a space where curiosity is disciplined by rigor and speculation constrained by data. In this way, Planet 9 becomes emblematic of modern astronomy. It reflects a field increasingly concerned with what cannot yet be seen, but can be inferred. Dark matter, early galaxies, distant exoplanets, and gravitational waves all followed similar trajectories from prediction to confirmation. Planet 9 follows this lineage, regardless of its eventual outcome. The enduring importance of Planet 9 lies in how it connects multiple scales of understanding. It links the motion of tiny, icy bodies to the architecture of the solar system. It connects local dynamics to galactic context. It bridges observation and theory. Few hypotheses achieve such breadth. As telescopes continue to improve and surveys deepen, the question of Planet 9 will move closer to resolution. It may be found, adding a new world to the solar system's inventory. It may be ruled out, refining understanding of distant orbital dynamics. Either result will represent progress, not loss. What will remain is the lesson that exploration is never finished. Even familiar systems contain layers yet to be understood. Even nearby space holds mysteries shaped by distance, time, and subtlety. Planet 9 reminds us that the universe rewards patience and curiosity in equal measure. In the end, the search for Planet 9 is not just about a planet. It is about how knowledge advances when evidence is incomplete, how understanding grows through inference, and how the unknown continues to shape inquiry. It is a reminder that science moves forward not by declaring maps finished, but by returning to their edges. And at those edges, where light fades and gravity whispers, the universe continues to invite exploration.